Hey, what's up, everyone? So my name's Rob, and this is a course on an introduction to statistics for the psychological sciences. And today we are going to dive into the 11th lecture of the course. So this is going to be on the concept of statistical power. What is it? How do we obtain it? A lot of this is going to quite naturally flow from our previous lecture on null hypothesis significance testing. And then, so we're going to talk about the concept of statistical power today. This lecture will actually be relatively short. And then in the next lecture, we're going to go into what I would consider to be probably the most important lecture of the class, which is on the central limit theorem. In your textbook, they classify it as, it's the chapter on sampling distributions. But so without further ado, let's dive right in and figure out how we can have the power. Okay. So what is statistical power? Well, statistical power is the probability that we will be able to reject the null hypothesis when the null hypothesis is false. Right? Now, another way to say that is it's the ability to detect an effect when there is an effect. So we really want to know this. We want to know, like, how, I mean, you can think of it almost as if, your statistical power is almost like the magnification level on your microscope. If we know there's an effect out there, and we have a sense of how big that effect is, right? Our statistical power tells us how well, what the likelihood is or the probability is that we'll be able to detect that effect with our statistical test. So now power, it is a probability, which means that it's going to vary from 0 to 1. The higher the statistical power, the more sensitive we are, the more ability we have to detect a real effect. So let's think about this. Like, say we wanted to explore whether or not our gratitude meditation, right? We randomize people so that some people get gratitude meditation and other people get some kind of active control meditation that shouldn't have gratitude in it. And we want to see if that influences their well-being or their self-esteem or something like that. Power is basically how sensitive are we at being able to detect whether or not our independent variable, the meditation type, will cause a real effect in the dependent variable, self-esteem, right? And so typically rule of thumb is we want to design experiments with a power of about 0.80 or higher, right? Because basically this means that we've got an 80% chance, a probability of 0.8 of detecting an effect when there actually is one. So ideally we would like power to be higher than 0.80. That would be tremendously desirable. But as we will see when we dive into this, that can be very constraining just in terms of how practical it is. So what is it like? What is power mathematically? Right? Oh, here's Skeletor. So power represents the probability of correctly rejecting the null hypothesis. Right? It's another way of saying we found an effect. Remember, the null hypothesis, when we reject the null, we reject it and provisionally favor the alternative. And that alternative hypothesis is typically what the researcher's predicting will happen. And so we talked about In the null hypothesis lecture, we talked about, or the null hypothesis significance testing lecture, we talked about alpha as being the symbol for a type 1 error, and beta being the symbol of a type 2 error. And just to recap, right, a type 1 error is a false positive. It's erroneously saying that our independent variable had an effect on the dependent variable when really it didn't, right? So we're saying that something's going on whenever actually in reality nothing's going on. So that's alpha. Beta is type 2 error. This is a false negative. It's not rejecting the null hypothesis whenever you should. This is, you do all this work, you design this study, you get all these participants, you go through the whole hassle of analyzing all the data, and your statistical test says, nothing's happening. When in reality, that's actually true. Now, which is worse, a type 1 or a type 2 error? Well, it kind of depends, right? It depends on the situation. There are certain situations where you might want to protect against a type 1 error more than a type 2, or vice versa. And so it just really depends on the context of what's most important to protect against. So beta is the symbol for a type 2 error, or a false negative. Power, so again, false negative is saying we didn't get an effect when there actually was one. Beta is the inverse of that probability, right? So if you take 1 and subtract beta from it, we get power, which is the tendency to say that you have a significant effect when there actually is a significant effect. Another way, just flipping it around, power plus beta is going to always equal 1, right? So it's, in this context, power is when you successfully say that you've found a real effect, and beta is when you don't successfully say that you found a real effect. So that is how those work. So the important thing is we want to maximize power because we want to give ourselves the best chances we can to find a significant effect if one exists in reality. And just think about all of the work that is involved in conducting a scientific research study, from developing the hypotheses to creating all the materials to hiring the people to sending it to the internal review board, the IRB. It's like the ethics board. Then collecting the data, then analyzing the data. You're putting all of this time and effort in, and you want to make sure that you are adequately powered so that you give yourself the best chance of finding a significant result, if it exists. So how do we increase power if that is a goal? Well, there's really two ways. The first way is we can increase the size of our sample. So we have a population that we're trying to study, and to do so, we randomly select a sample of people from that population. If we take a larger sample from the population, say instead of having 20 participants, we have 200, right? That is going to dramatically increase power. You can think of it as if the more people you have in your study, the more powerful your microscope is to detect an effect. Another way that you can increase power is to study effects that actually exist and that are sufficiently large, right? So let's think of an example of that. I doubt many people, like if we had you go through a haunted house, for example, many people would probably experience increased heart rate, right? If people are jumping out at you trying to scare you, that's going to be a huge effect, right? I mean, it's going to be a really big effect. But if you wanted to study something more subtle, right? Like something about, I don't know, how, even like, how haunted houses maybe increase people's desire for candy, right? That's probably not in reality going to, the haunted house is probably going to be have a weaker effect on desire for candy than it is on fear or heart rate, right? So you want to study effects that are sufficiently large, right? Because now it doesn't mean that you can't study subtle effects. It's just that you need a much powerful microscope. And that means you need a lot of people. And that can be prohibitive in some cases. Okay, so let's talk about power and beta again, right? So beta is the probability of a type 2 error, of a false negative. So power is going to be equal to 1 minus beta, or power plus beta equal 1. And what power represents is the probability of rejecting the null hypothesis when the null hypothesis in reality should be rejected. So now an interesting thing here is, now that we understand this relationship between power and beta, well, how do we know what beta is? Well, I mean, there are some fancy ways that you can figure it out, but really, we know that there is a tension between beta and alpha. So just think through this logically, right? The probability of saying nothing is going on whenever something actually is opposed to the probability of saying something is going on when it actually isn't, right? So that the first is beta, it's type 2, and the second is alpha, type 1 error. So, like as alpha increases, beta will tend to decrease. And as beta increases, alpha will tend to decrease. In other words, the easier, right? So you can think of it as if the easier we make it on ourselves, in other words, the more we increase alpha, the easier we make it on ourselves, the more likely we're going to reject a null hypothesis when it's indeed false. But also the more likely we are going to incorrectly say something's going on whenever it isn't. At the same time, we can flip that and we can say if we reduce alpha, right? In other words, we make it more challenging on ourselves to say, oh, there's a significant effect here. The independent variable is affecting the dependent variable. We need, it's going to be much more, if we reduce alpha, it's going to make it much harder on us to reject the null hypothesis. As such, we're going to be much more likely to make a type 2 error. We're going to increase beta. It's going to be much more difficult to detect an effect that's really there. So you can see that type 1 and type 2 error are opposing forces. When we try to protect against one, we open ourselves and make ourselves vulnerable to the other. And so alpha and beta are highly related in this way. The difference is it's kind of challenging to compute beta, but we know alpha. The researcher sets alpha. Alpha, if you remember, is that arbitrary line in the sand where, like if we set our alpha of 0.05, that means we're interested in this this area of the tail where the tail is a proportion of 0.05%, and we need to push the mean. Here, let me draw this out. So alpha of 0.05, right? We're saying that this is 0.05%. And in order for us to find a statistically significant effect, we need to push the mean all the way over past this critical value. If it's 0.01, it's going to be way out here. It's a much smaller shaded region. And we have to push the mean even farther to say that it's a significant effect. So, and when I say push the mean, just imagine this is some kind of like population mean. And that is our sample. We need a sample mean that's so different from the population mean that it goes beyond this cutoff value. That cutoff value is what determines alpha. And so the researcher sets that. The researcher sets the criteria for when we are going to say something is significant versus not. The standard is 0.05, sometimes 0.01, but it all depends on the context. It depends on, how much are we willing to accept a type 1 error versus a type 2 error? And these are opposed. So, okay. So what is an acceptable level of power? Well, here we can see it depends. If you've got a sizable effect, like in psychology, we typically don't get very big effect sizes like the yellow line. Let's say an effect size of this green line. Well, you can see here that if you want a power of 0.8, you're going to need, what, about 150 people? Now, what if you're studying a very small effect? If you're studying a small effect, look at this red line. How many people do you need for 0.8? Oh, like 800 almost? So the issue here is that on one hand, it is never appropriate to conduct, well, I shouldn't say never, but most of the time, it is not appropriate to conduct a underpowered statistical analysis. It just doesn't make sense to do it, right? It doesn't make sense because you can't rely on it as much. You want to be adequately powered to detect an effect when there is one. And so sometimes, if you're trying to study something and you see, oh, I need 800 people, are you planning on coming in and running these participants through some 3-hour long experiment one by one? That might not be feasible. How many years is it going to take you to collect 800 people if that was how the experiment was designed? Right? So these practical considerations need to be taken into account. But the important thing is you just probably shouldn't study it, at least in the way that you are, if you're not adequately powered. If you're not able to study it, it's kind of like if you're not adequately powered, you just don't really have the right to ask the question. So here are just a reminder, right? How can we increase power? We can study bigger effects that are easier to spot. We can set a larger alpha, right? Which means that we are going to have a greater chance for a type 1 error, but a lower chance for a type 2 error. And the third way is we can increase the sample size. Okay, now when a experiment, what if the experiment fails to reject the null hypothesis? Meaning it says that, your experiment didn't work. There was no effect of the independent variable on the dependent variable. Well, we can never, under any circumstance, assert that the null hypothesis is true. We can't make a claim on the basis of a null effect. We can only state that there was not sufficient evidence to reject the null hypothesis. Right? So we don't say it's true. We just say we don't know. And see, that's kind of a problem, right? Is if you can't reject the null hypothesis, well, what do you conclude? Well, you learn nothing. Unless you're sufficiently powered. If you're sufficiently powered and you know that you have a high probability of detecting an effect when there actually is one, it can kind of bracket and put some confidence around that. If you had very high power and you didn't get an effect, it's more likely that the independent variable probably didn't have a large effect on the dependent variable. Okay, so this was a relatively short lecture, but I invite you to really soak this in. In the next lecture, lecture 12, we are going to be diving into the central limit theorem, and that is a tremendously important concept. So be sure to tune in for that. And I hope this is all making sense. And I look forward to seeing you next time. All right, later.